Alright, so the first question asks you here, which parallelogram do you think has the greatest area? And a lot of people will often say either number 1 or number 4 just because it looks fatter, for lack of a better way of saying a term. But let's see what really happens. So it says to find the area of the parallelogram for each of them using the parallelogram formula, explain what we use for the base and the height. So we know that the area of a parallelogram, let me get a pen here, we know that area is equal to base times height. So then the question comes down to what do you want to use as the base and the height for each of the triangles. So I'm going to go P number 1. So if I look at parallelogram number 1, the area, well, I can use my tools here to help me out. My base is, I'm going to use segment AB because that's easy to measure. We talked about that earlier, but it's easy to use my grid. I can get the distance across there and see that that's 4. And that's 4 units or 4 centimeters if we're going to be using the measurements with GeoGebra. And I want to get the height. So the height is the perpendicular distance from segment AB to its parallel side, which is segment DK. So I could use my perpendicular tool. So I can click on, and then click on point D and say, okay, there's my segment. And I'm going to go from D down to there to U. And I can say, okay, that's 1, 2, 3, 4, 5 units. So I know this would be a 4 by 5 parallelogram. So I would say this is 20 square centimeters. So let's look then at parallelogram number 2. Well, what's interesting about parallelogram number 2 is that it is actually a rectangle. All right, so we're going to come here, get the pin out, and if I count here, I know that since this is my right angle right there, I can just count across 1, 2, 3. I know this is 4, and then 1, 2, 3, 4, 5. This is 5, so this is also a 4 by 5, which is 20 square centimeters. So let's look at then parallelogram number 3. Well, this one looks way different. I mean, look how much it's shifted the way it is. It's got to be different, right? So, well, I'm going to use side LM again as my parallel side just to make life easy. And I can see there's 1, 2, 3, 4. So I know I've got that area is a 4. And let's see about the height. The height I know is that perpendicular distance. So I know in essence that because N doesn't line up between LM, I'm going to need to extend that line we've talked about before. And then I can make my perpendicular height from point N down to that line. And I can now count 1, 2, 3, 4, 5. Well, that's also 5. So that's also 20 square centimeters. Well, then let's get to this last one. It's got to be different, right? Now here, if I look, it's actually easier to make my height, my base be the left or the right side, the QO or ST, because of being able to count the boxes. So I'm going to say that my base, 1, 2, 3, 4, 5, I'm going to make it OQ. So here we go, parallelogram number 4. So my base in this case, I'm going to call 5. And again, I want the height to be perpendicular, so I can get my perpendicular line here. I'm going to do it from point T over to QO. And then I can count 1, 2, 3, 4. Well, here again, that's a 5 by 4. It is also 20 square centimeters. So here are 4 different parallelograms. They all look different. Some look quote unquote thin or fat or quote unquote straight or skewed, but they all have the same area. And I can even click on every single one of these to see that my areas are 20 square centimeters. Now, part of the reason this happens is if you look at them, they all, here I want to reset the image. Let me reset this whole page here. if I look at what's going on and why this works, especially for the first three, look at my two parallels, what I'll call the top and bottom. You see that all three of those parallelograms line up. Even OQ lines up with that. Give me that piece that tells me that and when I find the height, when I go and click the perpendicular height, I can see that no matter where I put it, it's always going to be 5 units to the opposite side. 5 units to the opposite side. So what I have here is this idea that because all I'm doing is just shift, I'm using what's called the shear principle. Uh, it's falling on the same line, it's just being stretched out, but it's still going to cover that same area. It's one of the really cool things you can find out with the area parallelograms, that if you can keep the two sides at the same height, it doesn't matter how much you quote unquote stretch the opposite sides, you will still end up with the same area.